Okay, good morning, everyone. So we were doing conditional variance, and this was the result we left last time. So we defined conditional variance, and is the variance of x given y equals to y, and that's the definition of conditional variance. If we use a new notation, mu x given y to be this. So earlier we used mu. Okay, so earlier we used mu for expectation of x. Now for the conditional we are using this notation. Okay, so we are also adding this subscript. Okay, to mean the conditional expectation. Okay, then the way it is defined is this. Okay, so there is like 3-4 lines of proof for that, so I let you do this. Okay, so try this proof on your own. Okay, so it should be straightforward, but this is something we should remember. In general, the variance of x, the usual variance that we know, not the conditional variance, then it was expectation of x squared minus expectation of x whole squared, right? Now here, note the changes, right? So here we are talking about variance of x given y equals to y, and this we say it's expectation of x squared. Okay, y equal to y remains the same. Okay, expectation x squared given y equals to y minus expectation of x given y. Okay, so remember that expectation, conditional expectation, it can be treated as a function of y if the condition is on y, because for every input that you put here, you get some output. Okay, so this can be treated like a function of y. If you talked about only expectation of x, then it is just a number. Okay, it's a number, it's a constant, and so on. But since we are talking about conditional expectation, we have seen previously, conditional expectation can be seen as a function of that condition. Okay, so in this case, the condition is y is equal to y. So that's why we write also this additionally mu y here. Okay, because it does depend on what condition was. Okay, so this is the formula that you should remember. Okay, we may use this in examples. Okay, so for instance, if we see this example, x, y be two random variables with joint PMF given by this, and let z be expectation of x given y. Okay, and v be the variance of x given y. So this is the conditional variance now. So this is conditional variance, and we have to find the PMF of v. We have to find the expectation of v, and we have to verify this identity. Okay, so this is an identity we want to verify in advance, although we have not proved this identity. So this is an identity that holds. So we may try to prove this later. Okay, so we may try to motivate this identity by this example first. So this is the joint PMF given to us. Now, what is the first question? So find the PMF of the random variable, so which is the conditional expectation, right? So what is the PMF of this? Okay, so so did we see this example before? Yeah, so I think so recall from previous class, what we had is like similar joint PMF was given to us, and then what we have found for this exact example is that x and y, I mean, yeah, we have found that x and y follow the Bernoulli distribution. Okay, so we have found before that x, y follow Bernoulli in the last class. Okay, in case you have not missed the last class, then you have to see those slides. So we have proved for this that x and y follows Bernoulli, and we have also found that x given y is equal to 0 follows Bernoulli 2/3. Okay, And what other things we have found is that x equal to 0 given y equal to 1 is a certainty. So this is like 1, okay, if you recall, and then variance of expectation of this. We have calculated also this before, and if we calculate that expression completely, then it will be 8/75. Okay, so this is something we did from the previous slide. Okay, so assuming this information, now we can go and find the PMF of the conditional expectation. Okay, so to solve A, so to find the PMF of V, so to find the PMF of V, we note that, so we note that V is a function of Y. Okay, so yeah, so V is a function of Y as well, just like the conditional expectation. Variance is also a function of Y. So we note that V is a function of the random variable Y, or more specifically, we can write V is equal to variance of x given Y is, so there are two possibilities for Y, so we can split this into two parts, just like we did in the previous class. Okay, so now we are finding PMF of this variance, right? So okay, so variance of x given, so what are the conditions of Y? We have conditions, are two conditions are there, right? Either Y equals 0, right? So this is if Y is equal to 0, and then another condition is that variance of x given Y is equal to 1, that is if Y is equal to 1, obviously. So what do we have now? Okay, so we have calculated before, like what is the probability of Y being 0. Okay, but Y follows the Bernoulli. Okay, so the probability that Y, so remember Bernoulli is like for 1, right? So okay, so Y equal to 0 will be 1 minus 2 by 5, so it will be 3/5, and Y equals to 1 is the 2/5. Okay? In Bernoulli, this stands for the Y equals to 1 values, right? And for the 0, we get by complement. Okay, so this implies what? This implies V is variance of x given Y, and this is, I just copy it, x given Y equals to 0, and this is with probability of 3/5, because Y follows. Yeah. Okay. So I thought there was a question. Okay. So please turn off your microphone. So this with, yeah, please turn off your microphone. Okay, so with for y equals to 0, it happens with probability 3/5. Okay, so this is because Y is Bernoulli. Bernoulli. Okay, I think we have a disturbance. Let us find the culprit. Okay, no. Okay, so Bernoulli, and then so this was 2/5. Right? This is 2/5. This is because of that, right? Okay. So what do we do next, right? So we have this, but we are supposed to like find the PMF, right? So remember, like what we will do, right? So PMF is about the probability, right? PMF is about probability, and also like what are these values? Like we are also supposed to find these values. So let us see what are these values, and then we are supposed to reverse this to get the PMF. Then we will say 3 over 5 for that value of v and 2 over 5 for that value of v. Okay, but okay, so let us see what are these, right? So variance of x given y equals to 0. Okay, so what is this, right? X given y equals to 0 is a Bernoulli, right? And the variance of Bernoulli is what? Right? So we have to recall the variance of Bernoulli now, because this follows. So let us see this. Okay. So now since x given y equal to 0 follows Bernoulli 2/3, right? So this implies. So we are talking about variance of a Bernoulli, right? So variance of a Bernoulli is what, right? So variance of a, so if x is Bernoulli with p, then the variance of x is how much? P1 minus p, right? So we can verify this, right? So these, so let us see this. So Bernoulli 2/3. So this is P1 minus P, right? So this is like 2/3 and 1/3. So this is like 2/9, right? And what about the and we are so this is done, and then we need this, right? So variance of so let us see that. So given y equals to 1 and x equals to 0, so we have okay. Now given y equal to 1 and x equals to 0, right? I mean, let us see what was this x given y. So our focus is x given y, right? X given y equal to 1. Let us see this. Look, x given y equal to 1 happens with probability 1. And then this would imply that x1 given y equal to 1 will be 0 because this became deterministic now. So the probability of this happening, oh sorry, this is 0, right? So probability of this happening is now 0. Okay. Okay. So so this, if you look into this random variable, then this random variable has a deterministic value, which is just one value of x, right? So this takes only one. This forces it to have only one. Sorry, 0. Okay, this forces it to have only one value because this probability is coming out to be 1. So this means that this is just a point value, right? And this is exactly 1. Okay. So this is defined only for x equals to 0. This random variable x given y equal to 1. This is defined only at x. I mean, this is defined in the sense like this is making sense, or it is taking non-zero probability only at x equals to 0, which is 1, and remaining obviously it's like it's 0. Okay, because so the variance of this guy is going to be 0 because there is no spread at all, right? Because there's just point value it's taking. The variance is just a spread, right? So of course you can apply formulas and so on, but we know that the variance is going to be 0 here. So we have the variance of x given y equal to 1 must be 0. Okay. So all this implies if we now see this guy, right? So we have computed this and this. So we have computed the values of the of these v, right? So let us see this here. So now this implies v, which is variance of x given y, and we split this values of v into two parts when y equal to 0 and y equals to 1. And then we know that now y equal to 0 happens with some probability and y equal to 1 happens with some probability. We were left with computing these actual values. These actual values are now computed, so which is like 2/9 if this happens with probability 3/5. and 0 with probability 2 over 5. These are just copied from here, 2 over 5, 3 over 5, and this turned out to be 0, and this turned out to be 2 over 9. Okay, so now PMF is just like you just put this 3 by 5 front and then 2 by 9 on the other side. Okay, so the PMF value of V is now the probability. So 3 by 5 when V is if V is 2 over 9, and this here is 2 by 5, probability 2 by 5 if V is 0, and then you can define 0 otherwise. Okay, so because the sum is already 1, so anything else must be 0 now. Okay, so we found the PMF of V. Okay, so that question is now done. Now we are supposed to find the expectation of V. So this is just one line, so I can write it here. So the expectation of V is the values of V times the probability of V, right? Probability taken by that, right? So this is like 2 by 9, 3 by 5 plus 0 times 2 by 5 plus 0 times otherwise, so that is 0 anyway. Okay, now the C was variance of X is equal. So we have to verify that variance of X is equal to expectation of V plus variance of Z. Expectation of V we found it. Okay, and variance of X also we can find, and variance of Z we found before. Okay, so what we are left with is actually variance of X. So variance of X is, yeah, so variance of X will will come out to be the PMF values and the X values for that, right? So what is the variance of X now? So PMF values are given to us, right? So the variance of X will be how much? I mean, not even PMF, like something else is given to us directly, right? This actually. So we don't even have to do anything else actually. Just look at this. X, Y were proved to be Bernoulli 2 by 5. So now it's a matter of Bernoulli, variance of Bernoulli, right? So variance of Bernoulli is how much? 2 by 5 and 2 by 5 times 1 minus P, right? So P1 minus P, right? So variance of X will be 2 by 5, and then 1 minus of this will be 3 by 5, right? So this will be 6 by 25. Okay, so that's the variance of X we got. And expectation of V we have just found. So this is 2 by 15. Okay, from here. And variance of Z was 8 by 75. 8 by 75 is here. 75. So now the question is variance of X is equal to expectation of V plus variance of Z. Variance of X is equal to expectation of V plus variance of Z, right? So variance of X is like 6 over 25. Is this equal to expectation of V, which is 2 over 15 plus 8 over 75? Okay, this is 75. 15 like 5 times 10 plus 8, right? So this is like 18 over 75. So 3, 6, and 3, 25, right? Okay, so this indeed verifies that this is true, right? Okay. There is something called law of total variance. We have seen law of total probability, we have seen law of total expectations, and then we have now law of total variance. Let x and y be two random variables. The law of total variance says following, where variance of x is equal to expectation of variance of x given y plus variance of expectation of x given y. Okay. Okay, so a proof of this we need. Okay, so let us use some shorthand notation to just use. So let v be variance of x given y, and let z be. So these are shorthand notations. Z be expectation of x given y. Then v is the variance of this. Now remember the variance formula for the conditional variance, right? We just did in the beginning of the class, right? So this is expectation of x square given y minus expectation of x given y, right? And this whole squared. Okay, and this is equal to expectation of x square given y minus, and this is according to our notation, this is z and squared. Okay, so okay, and then we are supposed to find expectation of v, right? This is the first term. So let us go ahead and find the expectation of v. So expectation of v is expectation of x square given y, all right, minus expectation of z squared. Okay, so remember what is this? So what am I going to use? Two expectations, right? Applied on the conditional. Remember what was this? Okay, remember this LOIE. I'm not going to tell more. So according to LOIE, so we have so this will be just expectation of x square minus expectation of z square. Okay, we have found the expectation of v, which was this guy, the first term we found. Now we will focus on this guy, second term, right? So this was the first term, and then the second term is variance of z is now the usual formula, right? So expectation of z square minus expectation of z whole squared, and then this is expectation of z square minus, and then we substitute this, and then again LOIE. Okay, so this is like expectation of x given y, bracket close, and then whole squared. Okay, so this is expectation of z squared minus, okay, LOIE. Okay, so this is just expectation of x whole squared, right? Okay, and then yeah, so then we have to like verify now. So what is so first plus second term? Okay, so this is expectation of v plus variance of z. This is expectation of x square minus expectation of z square plus expectation of z square minus expectation of x whole squared. Well, this cancels, and this is nothing but variance of x. This is what we were supposed to prove, and this is indeed the LHS, and this was the RHS, right hand side. Okay, so this is the proof. Now let us move on. Okay, let us now do some solved problems in this chapter. So what is this chapter we are working on? Maybe you have forgotten what chapter we are in now, right? We are in the chapter of joint discrete random variable, right? Joint discrete random variable. Remember that we have not done joint for continuous yet, right? So, so there will be a continuous version of that, and then we will go into calculus, right? Integration, double integration, okay, partial derivative. Okay, so far, so we are trying to wrap up now. Okay, so in the joint distribution, discrete random variable, we have seen joint PMF, joint CDF. Okay, we have seen conditional expectations, we have seen conditional variance, we have seen law of iterated expectations, LOI, and then law of total variance, law of total expectations for the two variable case. And when I'm talking about joint, then so far we are only talking about two random variables. Okay, and then our next step will be naturally multiple random variable, and then we will talk about vector of random variable. Okay, so okay, let us go step by step. Okay, so X and Y, so this is the set of some solved problem in this chapter now. Okay, so we will solve some problems from this chapter. Okay, so let us see problems like this, where let us say we are given X and Y to be two independent random variables with the same CDF. Okay, so the CDF is like given to be the same fx and fy, and let Z be defined as this, and let W be defined as this. Okay, so here a natural question is like, if the CDFs are same, are the random variables going to be same? Okay, so that's already a thing to ponder about right now, right? I told that X and Y be two independent of the same CDF. Does this imply X is equal to Y? Well, naturally it should not, because otherwise I should have taken XX, right? Okay, so same CDF does not imply same random variable, but ... Okay, so you fill in the blanks, right? And okay, so let us move on and see. Let Z be max X comma Y and W be min X comma Y. So these are functions of random variables, obviously, random variables X and Y. So now we are talking about functions of random variable, and we want to find the CDF of the functions of random variable, in this case Z and W. Okay, so let us move on and see what we can do about this. This will follow from classical definitions. Okay, so CDF, we just write down what is the CDF of Z, right? So let us write down. So usual notation is capital F subscript capital Z and then the small z. So this by definition is probability that Z is less than equal to Z. Okay, and we just substitute the value of Z here. So this is probability that, so Z was defined to be maximum of X, Y, and this is less than equal to Z. Okay, this is like small z. Okay, so let me let me use small z here. Okay, and we try to resolve this inequality, right? So we try to resolve it because what is given to us is the CDF of X and Y. So obviously the answer will be in terms of the known quantity, which is, let us say, some given fx and fy. Okay, so in other words, our plan is to break this into the known quantity, which is the probabilities that involve only x and probability that involves only y. Okay, so now the question is, how do you break this inequality, right? So maximum of two quantity is less than equal to z. So this inequality is equivalent to what, right? So this inequality will imply what? Right? So maximum of two quantities is less than equal to z. Then what can you say about x and y individually, right? So what can you say about x and y individually? Well, I can be sure to say that this is this, and y is less than equal to z. Okay, so I'm sure about that. So this is what we are going to use here. So max of this is less than, then this does imply that x is less than equal to z, and y is less than equal to z. Okay, and well, and what is the next thing I'm going to use? Because I still see an end here. So what is it here that will help me to break it further, right? So what do you think? What furthermore is there for me? Okay, I see CDF, same CDF, and blah blah. Oh, I also see independent, right? Okay. let's see. So and will break, okay, because of the independence. The and is like a comma, right? Okay, so this is like probability that x is less than equal to z, and probability that y is less than equal to z. Okay, and what else? So here, so this is like f x z. This is the CDF, and this is f y z. Okay, I mean they have the same CDF anyway. So and it's just the notation is changing, right? And this happened because x and y were independent. Not where, they are. Okay, why should we put it in the history, right? Independent. Okay. Okay, so we got this into the known quantity, right? So that's done. Now we similarly we want to find the PDF of W, right? So PDF of CDF, right? CDF of W, and let us say a small w here. So this is probability that W is less than equal to W, and in this case we have to do a little bit more work because this is a minimize, right? Minima of x comma y and then less than equal to W. Okay, now what do we do now? So what do we do now? So we have to remember, we have to break this into individual parts, and then we can write this as individual product, right? So what am I supposed to do now? Probably the minimum x less than equal to W. How can I break this quantity further, right? So like minimum is, so we need Mentos, right? For दिमाग की बत्ती बुझा दे, right? So minimum of x comma y is less than equal to W. What do we need? Minimum of x comma y is less than equal to W. Okay, and but we are supposed to like split this, right? I am okay. If we reverse this inequality, what do we get, right? We can reverse this by doing 1 minus, but if we reverse the minimum is greater than, then individually they should be greater. Yes, that's correct, right? So first step is to step 1, reverse the inequality. So reverse will happen with probability. So this guy will be equal to 1 minus probability that minimum of xy greater than W. So that's the complement of this guy. So and hence we have, that was step 1, and step 2 will be, yeah, so minimum is greater than, individually these guys should be greater, and then we have to convert it back to CDF. So the CDF is given in terms of less than equal to. So x greater than W we have, y greater than W we have, then we have to change it back to less than equal to. So we have to take the complement. So 1 minus p of x less than equal to W, and then similarly here. Okay, we got this, right? So let us write it here. So this is 1 minus p minimum of x, y, and this is greater than W. So we took the complement. So that's what the probability says. And okay. And then what we found here is 1 minus probability of, so minimum is greater than, individually they are greater, right? So x greater than W and y greater than W. Done. Okay. So, and then here, so this is 1 minus, and then they are independent, right? So that's the next step. So they are independent, so they will split. So probability that x greater than W and probability that y greater than W. Right? Independence is very interesting property. In fact, we will use this independence property to prove some of the most important theorems. Okay, so this is so far we are here, and this can be changed, like I said, because we want to get the CDF. So CDF must be x less than equal to W. So we need to take 1 more 1 minus, right? So 1 minus probability that x less than equal to W. This x is capital X here, okay? And then this is a product. Oh, okay, this is a product. So again, put 1 more, and then this is 1 minus probability that y less than equal to W. Okay, So now we have this, right? So 1 minus, and this is the CDF of CDF for W. I mean, yeah, and then this is like 1 minus CDF Y, right? This is Y, okay, and W. Okay, so if we write this down, then this is fxw plus fyw minus fxw fyw. Okay, so so we can leave it here. Okay, so this is the CDF of the functions of the random variable here. Okay, so we can keep this here. Yeah, we can try a problem. Let us say this: x and y be two random variable, and the range is given to be the lattice points z square and subject to I to 1. Right? The joint PMF in this case is given by this guy. Okay, and the question is like plot Rxy in the xy plane. So basically we have to plot this guy. Find the marginal PMF. Okay, marginal. We are given the joint, so we have to find the marginal. Find the conditional probability. Find this probability. Find x is equal to y. So probability when x will be equal to y. And find the expectation of x given y equals to 2. Okay, so let us try to solve this problem. So the first question is to plot this, right? So I minus j is less than equal to 1, ij greater than equal to 0. And yeah, these are coming from the lattice point. So these restrictions will, this means that I and j, I minus j are lying between -1 and 1, right? So this gives us a hint of what are those points that are going to be satisfying this quantity, right? So let us see that. So the first thing is to plot, right? So to plot, what we have is the following. So we have this, and so let us say these are the points we have, and here we have these points, the latest points we need. So so I minus j is less than equal to 1. So I minus j equal to 0. I is equal to j is allowed here. So I equal to j will be the line passing through the origin, right? So I equal to j are these points here, right? So let me like, okay. So assume that this is like this. So these are the I equal to j line, and then the, so I could be just one more and then one less. Yeah, within the bandwidth of like 1 on above or below. Okay, and so only positive sides will be noted, so not the points below. And similarly, like we have these guys, and we have these guys. Okay, so these are those points which satisfy I minus j is less than or equal to 1. Okay, these are the points. Okay, so this is the plot of range xy. Okay, the discrete variables. Okay, and find the marginal PMF, PMFs pxi and pyj. The marginal PMF. So what is the definition of the marginal PMF? We have to like sum, right? So marginal PMF means like we have to sum over these values. So let us see. And in this pictorially, like what do you think? What is the sum? Like sum over which way, right? So it's already like a matrix form, right? So if you sum over this y, okay, or if you sum over the x values, then you get the y for that. And then if you sum over the column wise, then you get y, and if you sum over the row wise, then you get x. right? This is what we saw in some tabular data that we got, and this is what we are going to do if we want to get the marginal with respect to, yeah, so if you're going to get the marginal with respect to x, then we have to sum along the row. Okay, so the question B is, and due to symmetry, you can already claim that x and y must have the same marginal because of the symmetry. Okay, anyway, but we don't have to rely on that intuition. We can actually write down explicitly. So let us find the marginal. So px0 will be the joint 0 0, okay, plus pxy 0 1, okay. So since we are given 0, so the and x and y are greater than equal to ij are like greater than equal to 0, right? So the only values I'm supposed to have is now 0 0 and 0 1. I cannot do 0 2 because that will violate 0 minus 2 less than equal to 1. Okay, so that will not satisfy. So that's why I stop here. Okay, now so px. And then we also want to know what is the size of the sample space. Okay, so how many points are there in the sample space? Well, you count all possible values for this, right? So 0 0, okay, and then 0 1, right? And then yeah, so 0 2 is not possible now. So 1 0, 1 1, okay. What other values are possible here? So how many points we are going to have? So, but you see, this is a line that goes up to infinity, right? So like there, I minus j greater than equal to less than equal to 1. If we see, this will keep going, right? But we are talking about this case, right? So what do you think will be the probability of 0 0 now and probability of 0 1? Okay, so what do you think? Because like once you, yeah, like once you have this 0 value, there is some kind of conditional going on now, right? Because once I have the 0 value, and well, the probability values are given to you. Actually, I don't have. We will just read out from here. I don't know what I was thinking. We have to write the probability, right? And PMF value is okay. So let's see. 0 0, right? So 0 and 1 over 6. Okay, so this is just 1 over 6 plus. So I was like wondering, do I have to find the PMF myself? But thank God I don't have to, because this is already given to me. And then pxy 0 1, right? So the minimum will be again 0, so it will be again 1 over 6. Okay. So this is 1 over 3. Okay, so B is and then px1. Okay, so what are the possibilities when? So we have to take the joint, and what are the possibilities we have? 0 is a possibility, and 1 1 is also a possibility, because 1 minus 1 is 0, and then what else is a possibility? 1 2, right? Okay, so these are the only possibilities, and in this case, what do we have now? So this is like so this still remains 1 over 6 plus pxy 1 1, right? So 1 1 minimum is 1, so 1 by 12 plus minimum is 1, so 1 by 12. Okay, so this is 12, 2 plus 1 plus 1, 4 by 12, and this is 1 over 3, right? Okay, and then we can compute 2 because margin, we are computing marginal, so we are listing out the values that we have. And remember that it's not going to stop, right? We are, with this, we are only finding the pattern right now. But, oh, is this, yeah, this is correct, right? So we are only finding the pattern because x will go up to infinity, right? But we are trying to find a sequence and we can write it compactly. So P2 is how much, right? So again, we go to the joint. So 2, 0 is a 2, 0 is not a possibility, right? So 2, 1 is a possibility. Pxy 2, 2 is a possibility. Plus Pxy 2, 3 is a possibility. Okay, that's all. And this is 1 over 6 or 1 over 12, right? Because this 2 is there. Plus, okay, 2 is there, right? So 2 to the 2, so 4. So 4 and then 6. So 24, right? So 1 over 24 plus 1 over, minimum is again 2. So 1 over 24. So 24, 24. And so this is like how much? So this is like, yeah. So this is like half of 24. And this is like so many of the 24, right? So that will be like 1 over 12 basically. 1 over 12, right? Or 1 over 12 or 1 over, let's see, 1 over 2 of the 1 over 12, right? So this is like 1 over 6. Okay, and then probability of 3 is Pxy 32 plus Pxy 33 plus 1 over 24 plus, now minimum is 3, so 8 will be there. So 6 times 8, right? Plus 1 over, again 6 times 8. So this will be 1 over 6 times 4, right? 6 times 4. 1 over 4 plus 1 over 8 plus 1 over 8. Okay. So this is like 2 times 1 over 8. So 3 1 over 8, 4 1 over 8, half is 1 over 12. Okay, so what do we see, right? So we have to find the pattern now. So for 0, 1 over 3. For 1, it's 1 over 3. For 2, it's 1 over 6. For 3, it's 1 over 12. Right? So what is going on? Right? 1 over 3 for 1. So this is like, but then this is like 2 times 3, right? So this is like 1, 2 times 3. And here it is what? 3, 4 is 12, right? So 3 times 4. Okay, 4 can be written as 2 squared, right? Okay, so it seems to be in this form, right? So each time there is a 3 and then there is some power of 2. So 2 will be, and then that power of 2 is that argument minus 1. Okay, so in general, we can verify this. Okay, so in general, we have pxk, and by you can also do a calculation for y. Okay, so this is like check by symmetry. For the moment, by symmetry, we just write this, that this is also equal to py, and this is 1 over 3. So k equal to 0 is the special case. Okay, 0 minus 1, that will not fit in our formula. So that we keep it separately, let us say. So when k equal to 0, and otherwise we suspect that this is 2 times k minus 1, and k is equal to 1 to so on. This is just to write things compactly. It's not that necessary for us to identify this form. Okay. Now okay, so this is done. This is done. Now we are here. So find probability conditional, right? X is equal to y given x is less than 2. So probability that x is equal to y given x less than 2. So this by definition is probability that x is equal to y and the joint. So this is comma here, x less than 2 divided by the probability that x less than 2. Now, okay. So x is equal to y and x less than 2. What are the possibilities on the grid, right? So x must be equal to y and x less than. So the possibilities are 0, 0 and 1, 1, right? So probability of 0, 0 plus probability of 1, 1 divided by probability that x less than 2. What are the possibilities? 0, and because x must be greater than or equal to 0 is this. Now all these values are known and you can do the computations. Okay. So it was how much? 1 over 6 was probability of 0, 0 by the definition of this. So 1 over 6 plus again by the definition of the same thing, it will be 1 over, because the minimum is 1, so there will be 2 here. 6 times 2 is 12. And px0 and px0 is just 1 over 3 from here. And px1 was also 1 over 3 from here. So 1 over 3 from here. Okay. So C is done. And then we can also do like this D part. Okay. Although these are like, they seem to be like, yeah, more or less straightforward, but just for completeness, maybe a practice I'm doing, I guess. I don't know if I leave this or not. Okay, 1 less than equal to x square plus y square is less than equal to 5. So this is the part, and then yeah, so you just have to calculate which are the values of x and y that will satisfy this. So this will be x y 0 1 and plus x y 1 0 plus x y 1 1 will satisfy this, plus x y 1 2 plus x y 2 1, and all this will be, so 1 over 6, 1 over 6, 1 over 12, because the minimum is there, so it's 1 over 12, minimum is 1, so 1 over 12, minimum is 1 again, so 1 over 12. Okay, so this is 2 of 1 over 12, 2 of 1 over 12, 4, 5, 6, 7 over 12. Okay. E was probability that, if you remember, what was that? Probability that x is equal to y. Okay, so probability that x is equal to y. So so this is, so sum those values wherever x is equal to y. So p x y I. Now I will go up to infinity. Now we need the joint value 1 by 6 times 2 to the minimum ij. Okay, so 1 by 6 times, so this is under summation I. It's going from, sorry, 0 to infinity, 0 to infinity, 6 times 2 to the I, because the minimum of I and I is I. Okay, if you compute this, what do you get? That's an exercise for you. And yeah, and then is it worth doing? Seems to be okay, right? Probably expectation of x given y is equal to 2. Okay, so yeah, so expectation of x given y equal to 2. Let us do this. So that was like E and F, right? So expectation of x given y is equal to 2, right? So to do this, first, to find expectation, you need to find the PMF of that argument of the expectation, right? We need to find PMF of x given y is equal to 2, right? So what is that? So let us try to find out x given y, and k2 given 2 is the joint xy k2 by probability that y is equal to 2. Okay, so k comma 2, right? And so what is this? Well, it remains k comma 2, but probability that y equal to 2 was how much? Y is equal to 2 was same as this guy, right? So y equal to 2 was 1 over 6. K is equal to 2, so 2 minus 1 is 1, so 2, 3 times 2 is 6. So this at least we know. So this is like 1 over 6, so 6 will go up. So pxy k comma 2. Okay. Okay, and from here, what do we know now? Restriction here because, right, isn't it? Because this is on the grid, right? So you since 2 is fixed, so k will be restricted to values 1, 2, and 3. So since x, or what is that, y, right? So y is equal to 2, k can be 1, 2, 3 only, right? K can be 1, 3 only. Okay, so that k is restricted by that. So this will save us in writing this compactly, right? So probability that x given y, k given 2 is, okay, so let us do one by one, right? So k is equal to 1. So k is equal to 1, minimum is 1, and 6 times 1 over 12, it is half, right? Half for k equal to 1. And k is equal to 2, so minimum is 2, so 4 is there. So 1 by 24, 6 times 1 by 24 is 1 by 4. K is 2. K is 3. Minimum is 2. Well, it's the same case, right? It's the same here. So 0 otherwise, because other values of k are not possible, so those must be empty events. Okay. And now, so we have found the PMF that we needed. Now we are ready to find the expectation, right? So this implies expectation of x given y is equal to 2 is now, yeah, so if y is equal to 2, what are the possible values of x? So x can take values 1, 2, and 3, right? So x can take values 1, and for that 1, the PMF value comes out to be half. And then x can take value 2. So this is 2 times, and then 2 given 2. So 2 given 2 was 1 over 4. Plus expectation can take value 3. And for that value of 3, it is again 1 over 4. And overall, this is 7 over 4. Okay, overall, this is 7 over 4. Yeah. Okay, no problem. Expectation can be more than 1, right? And variance now can be computed. So variance would be straightforward because expectation values are given to you, and wherever you have x square, right? So variance of x given y is equal to 2. So what was the formula for this? So expectation of you do this square, right? X square given. Okay, I think I should stop now. It's 10:30, so we will continue from here. In fact, you should do this as an exercise. It's straightforward, okay? Okay, I will stop here. I will stop the recording. It's already 10:31. Okay, thanks and bye. And you will have a quiz next week. And then yeah, I will specify the details up to which lecture it will be covered in the quiz. Not all the lecture will be covered in the quiz because it will be too much for you. So I will tell you the set of lectures starting from the first lecture until which lecture will be the syllabus for the quiz next week. Okay. So anyway, so yeah, see you next week. Yeah, see you next week. Bye.